Hi Math 2 students, this is Ms. Van Vickel, and this is Unit 6, Lesson 4, Modeling with Exponentials, and these are your lecture notes. This is the first video in a series of videos that will probably span Wednesday and Thursday for you. That's April 22nd and April 23rd. And we are going to examine exponential growth and decay with the percent formula. Remember in yesterday's videos, we were using y is equal to a times r to the t power. And we were talking about things that doubled or things that halved, like half-life. But now we want to work with percents that aren't exactly doubling or halving. We want to work with any percent, really. So we're going to work with a formula that looks like this. Now, let's examine each piece of it. Y, for example, could be the amount of money after a certain amount of time. A is the principal. It's still the beginning amount. So you'll notice it says the original amount that we borrowed or deposited. The interest rate is R, and it's a percent, but it's written as a decimal. And T is our number of years that we're using for the modeling situation. So let's work a handful of problems and see how this kind of revised formula for exponential growth and decay works for us. In example number 1, the population of Cary in 1980 was 21,763 people, and it has increased at an average rate of 91.36% for every decade, every 10 years. What is the population of Cary in 2010? So let's see if we can fill in most of our formula. We know that this is the number of people in the end. This is the number of people in the beginning, 21,763. That's our A value. And then we have 1 plus the growth rate. Notice we add when it's growth. We're going to subtract when it's decay. And we're going to write our percentage as a decimal. And then in our exponent, we want to have the number of years divided by 10. And the reason we do that is because we are growing at that rate every 10 years. So if we were to put in 10 for t, we would get 1 period of 91% growth. So that's why we want to divide our exponent by 10. Then it asks, what's the population of Cary in 2010? Well, I need to know the number of years between 1980 and 2010. And if that's easy for you to look at and say, well, that's 30, that's great. But if it doesn't occur to you immediately how many years, you can just do this subtraction and you'll end up getting 30 years have passed since 1980. And so 30 is what we're going to insert here for t. And we end up realizing when we put in 30 and divide by 10, we get 3. So I'm going to do this in my calculator. I'm going to take, I'd like you to be able to see both the formula and what I'm doing in my calculator. I'm going to take 1.9136 and I'm going to raise it to the 30 divided by 10, or you could just put in 3, power. And then I'm going to take that and I'm going to multiply that times our original amount, times 21,763 people. And that tells me that in 2010 there were 152,500 people in Cary. And I would probably take this 0.8 and round up, because it's kind of hard to have 0.8 of a person. So my answer here is 152,501 people in Cary in 2010. So that's the answer to the first problem. In the second problem, your uncle is going to sell you his 2009 Honda Civic for $3,090. He explains that the value of the car has depreciated at a rate of 20% per year since he bought it in 2009. But unfortunately, he can't remember what he paid for the car when it was new. To the nearest dollar, estimate the value for your uncle. Well, they're asking us to find A. What was the beginning value? And they're giving us the ending value. We've got 1 minus 20, because to depreciate means to decline. So we need to subtract the percentage of decline from 1. And our years is just t. They haven't given us any kind of alteration to our exponent in this case. So I know my value for t. The Honda Civic was new in 2009, and it's now 2015. So t is going to be 6 years since your uncle bought the car. So what I'm going to do is I'm going to sort out this by saying I have 1 minus 0.20, and I'm taking that to the 6th power. So what I have in my equation is 0.262144 times A is equal to 3090. And now if I solve for A by dividing both sides of the equation by 0.262144, I will get this. And that should give me the original amount that my uncle paid for the car of $11,787.41. So my answer is $11,787.41. And that should have been the original value of the car. So in problem number 3, it says you invest your first paycheck in a bank account that pays 1.2% interest each year. If you don't make any other deposits or withdrawals, how long will it take the money to double? So in this case, we're being asked to solve for a time period. Our initial amount is $135. And our bank is paying, so we're going to add 0.012. That's the decimal representation for 1.2% interest. And t is what we don't know, but we do know the ending amount. They said how long will it take the money to double? So we would have $270 if we doubled 135. Notice we're solving for t, and the way we always solve for t is graphically using our calculator. But before I do, I'm going to divide both sides of this by 135 because I always like to isolate the thing that I'm taking to a power over here on the right-hand side so I can graph it all by itself in y2. So let's simplify our equation. On the left we have 2, and on the right we have 1.012 to the t power. And this is what I'm going to be graphing in my calculator. So let's clean up our RAM a little bit before we go on. And I'm going to graph 2 in y1, and I'm going to graph 1.012 to the t power in y2. And I'm going to hit graph. And what you'll notice is these both look like lines. And I'm thinking, well, maybe I made a mistake and I didn't put the x in. But I go back to y2 and I see my x's right there, and everything looks fine about what I've put into my calculator. So then I realize that this is growing very slowly. 1.2% interest is not a whole lot. So maybe I should increase my x max, and I'm not sure what to increase it to, but I'm giving an educated guess of 100, and we'll see if we can see what we need to by looking at that. And what you notice when you increase your x max is you can kind of see that exponential function starting to move a little bit. And we could increase our x max even more and it would make more of a curve. But I think I'm okay because I can see my intersection is somewhere there. So I'm going to go second calc. I want to find an intersection. The first curve is in fact y1 of 2. The second curve is in fact this equation in y2. And I hit enter for guess, and it tells me that after 58 years, I will have doubled my money. So that is the answer to problem number 3. T is equal to 58.1 years, just a little bit more than 58. So the last problem that we have to consider in the first part of our modeling examples is problem number 4, where they're talking about March Madness. And we just finished March Madness this year. And it says that March Madness starts with 64 teams, and each round of the tournament, 50% of the teams are eliminated. And it wants to know how many teams remain after the third round. So I would just multiply by 1/2 3 times. But I could also model that with an equation saying I start with 64 and I get rid of half of them. Well, let me write this differently. I get rid of 1 minus half of them with every round. So in this case, T is going to be each round of the March Madness. And notice that because I'm eliminating half of them, I've got a minus sign here. That's important. If you put a plus sign, you'd actually be growing in the number of teams. So how many teams remain after the third round? I want to put 3 in for T. Y is equal to 64 times 1/2, and I'm just going to simplify this, to the third power. So I would use my calculator and I would say 1/2 to the third power, and then I would multiply that times 64 and find that 8 teams remain. So that's my elite 8 after 3. In answering number 4, it says if a team wins 4 games, they've made it to which prestigious level, and the answer would be Final Four. And the reason I know that is because if the third round is the Elite 8, then the next round would have to be the Final Four. And then it says how many games must a team win to be named national champion? We're dealing with such small numbers, you guys could probably count those up on your own. But I want to do it using an exponential model. So I would say that national champion means there is 1 team left. I started with 64 and I eliminated 1/2 of them every round. And now what I'm solving for is T. And so I need to know how many rounds we played to get down to 1 team. So I've been dividing by 64, dividing by the starting amount. So I'm going to divide both sides of this equation by 64, and I get 1 over 64 is equal to 1/2 to the T power. And again, because I'm solving for something in my exponent, I'm going to need to do that using my calculator. So on the left-hand side, I have a really small number, 1 divided by 64. And on the right-hand side, I have 0.5 to the T power. And since that's so small, I know that I'm going to have to make my y min and my y max really small. So let's do 0.1, negative 0.1, and 0.1. And see if we see what we need to. And I know that I don't have 100 rounds, so I'm just going to leave my x max at 10. And let's see what our graph shows. And I can see my intersection right there, so that's the point I want to find. And I'm going to again do second calc. And I think you've seen me do this enough, you don't need me to walk you through the steps. And it says after 6 rounds, I'm down to 1 national champion. So T is equal to 6 in this case, and I have solved for my exponent by graphing. So this is it for video 1 of Wednesday's videos on exponential growth and decay modeling.